Okay, so in this lecture, let us discuss the storage elements. So a storage element in a digital circuit can maintain a binary information. This we already discussed in the last class. Okay, so it maintain a binary state or binary information indefinitely. That means as long as the power is delivered to the circuit, it maintains the state. Or sometimes if you supply some external inputs, then its state is changed. Therefore, the output of the storage element is either changed by the input or the power supply. If power supply if you cut off, then the output definitely will go off. So the major differences among various types of storage elements are in the number of inputs they have it. Okay, how many inputs you are going to give it, and how you are going to control it. So these are the things. Based on that, you can classify the storage elements. So the storage element that operate with signal levels are referred to as latches. So how your signal levels are going to be applied. Okay, so these latches are controlled by a clock transition. Okay, how you are going to apply the input signals. Okay, sometimes the clock signal is used to control, so those are called flip-flops. So in latches we don't have any clock signal. So in this, no clock signal. In the flip-flops, if you have the clock signal. So that's a difference between your flip-flop and the latches. So latch is said to be level sensitive device. In the previous lecture, as I said, you have positive edge triggering and level edge triggering and trailing edge triggering. So these latches are sensitive devices. So it is like level triggering. Okay, level sensitive devices, latches. On the other hand, flip-flops are edge sensitive devices. Edge sensitive device. So the two types of storage elements are related to each other. Okay, so you can go from latches to flip-flops. In fact, if you want to understand a flip-flop, you should be very good in latches. Once you know the operation of latches, then it's very easy to understand flip-flop. So therefore, we need to start with latches. Okay, so let us start off latches. Now, although the latches are used to store the binary information and for designing sequential circuit, they are not practical for use as a storage element in synchronous sequential circuit. Okay, so either you can use latches or flip-flops, but still you can whatever you want to do with the help of flip-flops, the same thing can be done with the help of latches, but still people will not use latches in practice. The reason is they are the building blocks of flip-flops. See, you can build the flip-flops based on the latches, but we will not consider the latches for storing, we will not consider the latches as a fundamental storage mechanisms because it has some drawbacks that we will discuss as we go along. Okay, so latches will not be used in practice and we will not use it as a storage device. But you can use latches to construct flip-flop, and flip-flop is used to store the binary state. Now let us move on to SR latch. The meaning will be clear soon. LATCH latch. Now here this S stands for set and R stands for reset. So that's what it means. Okay, SR latch. So this SR latch is a circuit with two cross coupled NOR gates. So generally they will use two cross coupled NOR gates. Sometimes people will use two cross coupled NAND gates to construct the SR latch. And this SR latch has two inputs. It has two inputs. Those inputs are S and R. As I said, S means set and R means reset. That's it. Now let me show you the figure. Insert. Pictures. Then there are two types of and then yes, this is SR latch. Good. So now look at this figure. Okay, so I have two cross coupled NOR gate. So this is NOR gate 1, NOR gate 1 and NOR gate 2, and two inputs. This input is S means set and here R stands for reset, and two outputs Q and Q bar. And this latch has two useful states. So okay, when the output, the important point to analyze the circuit is look at the output. So I have two outputs Q and Q bar. That means what? The outputs are complement of each other. Like if Q is 1, then Q bar must be 0. So here if this is 1 and this must go to 0. If the upper point is 0, then the lower end will be 1, not other way around. So both cannot be 1 or both cannot be 0. That is not acceptable. So at any point of time, the output is always complemented. One will be 1 and other will be 0, or if this is 0 and the other will be 1. So this is the important point you should remember to analyze the state. Now when Q is 1 and Q bar is 0, this is called set state or set condition. Similarly, when Q is 0 and Q bar is 1, this is called a reset condition or reset state, or whatever it is you can call it. Okay, when Q equal to 1 and Q bar is when Q equal to 0 and Q bar is 1, it is in the reset state. So if you notice, as I said, Q and Q bar are normally the complement of each other. However, when both the inputs are equal to 1, let's say this is 1 and this also 1, then what is going to happen? Both the inputs are equal to 1 at the same time, then what is going to happen? This also equal to 0 and this also equal to 0, right? So in that case, both the outputs are equal to 0. Okay, and this is not acceptable. As I said, one has to be the complement of the other, but if you supply one in this reset and one in the set point, then both the outputs will be 1, and that is called forbidden state. That's what we have written here. So if both are 1 1, then it is forbidden state. Okay, if both are 1 1, then what is going to happen? Both the okay, so it will enter into 0 0. So therefore this is called unpredictable or undefined state. Sometimes people called metastable state. Metastable state or unpredictable state or undefined state. Undefined state. Okay, either you can call metastable state or unpredictable state or undefined state. Okay, so in practical applications, setting both inputs to 1 is forbidden. You are not supposed to give both the inputs to 1. You should give 1 0 or 0 1 or 0 0 you can apply, no issues. But at any cost you are not going to, you must not apply 1 1. That is why in the beginning of the class itself we will not use the latches as a storage elements. It has some drawbacks. Certain input conditions are not applicable in the latches. But this is not the case when you go to flip-flops. Okay. Therefore, under normal condition, like both, okay, let us analyze. Now, under normal condition, both inputs of the latch remain at 0 unless the state has to be changed. If you keep both the inputs 0 0, then the previous state will be maintained. Now, let us take the set condition. As I said, when S equal to 1, then R equal to 0, then what happens in this time? Your Q is going to be 1 and R is going to be 0. This is called a set condition. Let us analyze how this is going to occur. Or before that, I will not write down the Q value. Let us see how things are changing. Let's say I have given this condition. I applied S equal to 1 and S equal to 0. Now what is going to happen? When this is a NOR gate, right? In the NOR gate, if any one input is 1, then what is going to be the output? See, the NOR gate is OR plus NOT gate. Now A, B, two inputs 0, 0, 0, 1, 1, 0, 1, 1. So the output is, let's say output is 0, 1, 1, 1. Then output, if you take complement of this, 1, 0, 0, 0. That means what? If any one input is 1, the output is 0. See, 1, 1 output is 0, 1, 0 output is 0, 0, 1 output is 0, 0, 0 output is 1. So from this truth table of NOR gate, if any one input is 1, the output is 0. Now, in this condition, when S equal to 1 here, if any one input is 0, then output is 0. Therefore, Q bar is 0. As I said in the beginning, when Q bar is 0, then what is Q? Q is complement of Q bar, right? So this is going to be 1. So this is called a set state. So like that we need to analyze the circuit. Now let us take the reset condition. Now then if you apply 0 0, okay, so this is 1 and this is 0, this is called a set state, right? Set state. Now if you apply 0 0, then what is going to happen? No change. Okay, you can analyze, no issues. So this is 1 and this is 0. Okay, so previously it is 1 0. Now output is Q is 1 and Q bar is 0. Now you are going to apply 0 0 here. Now this one is coming over there, right? So in this point 1, if any one input is 1, what is output? 0. So it is moving from 0 to 0, right? Now since Q bar is 0, this 0 is coming over here, this is 0 and this is 0, both are 0. If both inputs are 0, what is output? Output is 1. Again you are moving from 1 to 1. So the state is not changed. So that is why, look at here, this is 1 0, 1 0. If you look at, if after 1 0, if you apply 0 0, then there is no change in the previous state. After S equal to 1, R equal to 0, again you are getting 1 and 0 in the output. So these two are called a set state. Set state, set condition. Fine. Now let us apply the next one. So if you are not able to follow this, just rewind the lecture and listen again and again. So the analysis you have to do it properly, otherwise you will get into trouble. Okay. Now let us say I am going to apply S equal to 0 and R equal to 1. Now this is 0, R equal to 1. Now you should start the analysis from this point, okay? Don't start with the set. Because for NOR gate, if any one input is 0, what is output? Output is 0. If q is 0, what about q bar? Q bar is 1. That is why if we give 0 1, 0 to s here and 1 to r, then output is 0 1. So q is 0 and q bar is 1. Now in this case again, if you apply 0 0, then no change will occur here. That also you can verify now. Okay, so you apply 0 0 here. Now q bar is 1, this one is coming all the way and it is applied here, feedback here. So if any one input is 0, then the output is 0, and this 0 is coming all the way here and this input is 0, and already set is 0, right? Both the inputs are 0, so therefore this is 0. If both the inputs are 0, then again output is 1. So 1 to 1 and 0 to 0. So that is why, see, 0 1. Previously it was 0 1, now also it is 0 1 once you apply 0 0. Fine, no issues. Now the trouble actually comes now. What is the trouble? So the trouble is when you apply 1 1, then there is a problem. See this, if any one input is 1, the output is 0, right? And similarly, if any one input is 1, output is 0. So q is 0 and q bar is 0. But as per the design, as per the circuit operation, the outputs are complement of each other. So this is not possible. So that is why they said forbidden state. So this is my function table of SR latch. And there is a logic diagram. And here we are using, of course, positive logic. Okay. So 1 represents positive voltage and 0 represents 0 voltage. Maybe this can be like 3 volts or 5 volts like that, and so on and so forth. That's how one can analyze the SR latch. Always start with the input where it contains 1, because you just remember the truth table of your NOR gate. Okay, so A, B and output 0 0, 0 1, 1 0 and 1 1. For this condition this is 1 and remaining all points this is 0. So if any one input is 1, output is 0. So therefore you look at the input which has 1, logic 1, then from there you start to analyze. It's very easy to analyze this flip-flops. So if you are good enough in this understanding, then we will move on, because this is the basic building block. Based on that only the subsequent topics are going to be discussed. Okay, now for example, if I set s equal to 0, s equal to 1 and then r equal to 0. How will you analyze? Don't start from here, okay? Don't start from 0. If you start from 0, then you will be in trouble. Okay, so always start from the input which has 1. See, this point is 1. This point is 1. If this is 1, the output is 0. It's very easy for you. If this is 0, then this 0 is coming here and both inputs are 0, therefore output is 1. That's it. Finish. Or else, in case, just for the sake of discussion, if you start from here, if you start from reset point, this is 0. Now we don't know this one, okay? Then you have to look back here. So we don't know what is the output now. So we don't know. Okay, so you will be in trouble. So we need to know, look at what is the Q bar and all those things. Okay, don't bring all this unwanted complications. Always take the easy part. If any one input is 1, then output will be 0, that's all. So therefore start the analysis from that particular point. In case if I give the combination like this, let's say reset is 1 and set is 0, then start the analysis from here. So this is 0, if Q is 0, then Q bar is 1, that's it, finish. And you can enter the truth table, that's all. Fine. Now let's move on to the SR latch. But now this time I am going to construct the SR latch using Nand gates. So insert picture Nand gate. Where is it? This one? I don't know. Draw. Insert pictures. I think this guy. Done. Yes, wonderful. Now again slight modification we need to do here. Now this figure contains again SR latch, but this time we are using NAND gate. Okay, now again this also cross coupled connection. Why is it called cross coupled? Output of Q is connected to the input of the second NAND gate, and output of the second NAND gate is connected to the input of the first NAND gate. Okay, that's why this is called a cross coupled NAND gates. Now this also operates like more or less with the SR latch, but slight modification here. Okay, it operates with both inputs normally at 1. So here this 1 is possible, here 1 is forbidden, right? So in this case 1 is allowed, but 0 is forbidden here. That's a problem. Again, so you try to get rid of one problem, but you are entering into other problem. So that's how the technology has evolved. So initially people developed one concept and they faced some problem. Again, some other people came at a later stage and they thought some other solution and they removed that drawback and they developed the new one. Right. So initially people thought, okay, let us construct the SR latch with a NOR gate, but there they faced the problem of 1 So 1 is forbidden, so you cannot apply. In case if you apply, then the circuit will not work, it will start to malfunction. So then, okay, why can't we stop at NOR gate itself? Let's move on to NAND gate. So again NAND gate also they faced some problem. So how do you overcome that? Next level, that's it. So like that the things are evolved. Okay. Now look at here. So there is a difference here. In the previous case, the S was in the down. So zigzag. See in the cross. In the down S, set input in the top end is Q. But here the top end is set and the top end is Q. So that's a thing you should remember in this case. Now when you put S equal to 0, then what is going to be your Q? Let's say S equal to 0 and R equal to 1. Now how do you start the analysis? In the previous case I said you start from the 0. When any one input is 0, then output will be 1. That's what I said, right? Now in the NAND gate, you know the truth table, A, B and output. Now if both the inputs are 0, 0, output will be 1. 0, 1, output is 0. 1, 0, output is 0. 1, 1, output is 0. So if any one input, no, what did I do? I'm sorry. This is 1 and this is 1. Now if any one input is 0, the output is 1. Wonderful. Now this is 0 and this is 1. Start the analysis from here. If any one input is 0, therefore the output is 0. So yes, Q is 0. If Q is 0, Q bar is 1. This is called a reset condition. Or else let us go properly as like in the function table. Okay. Now here look at the function table. This is 1 0, right? S equal to 1 and R equal to 0. When S equal to 1 R equal to 0, how do you start the analysis? Start from the 0 point. When the input is 0, if any one input is 0, then output is 1. Am I correct? Yes. Yes, output is 1. If Q bar is 1, then Q is 0. So that's what happened. Q is 0, Q bar is 1. Okay. So S equal to 1 and R equal to 0, then this leads to Q bar is 0 and Q bar is equal to 1. Now if you apply 1 1, now if you apply 1 1 to this and here also 1, now with if the input is 1, you cannot analyze. Okay, so you need the second input also in this case. If any one input is 0, yes, you can go ahead and you can find the output. But if one input is 1, then you need to know the second input also to find the output. Now look at here. This is 0, this 0, this point is 0, this is coming over here, and this is 0. One input is 0 and the other input is 1, therefore output is 1. This 1 is coming over there, and this is 1, and this input also 1. So both the inputs are 1, so the output is 0. So no change from the previous state. So previously it was 0, 1. Previously it was 0, 1. Once you apply 1, 1, again it is 0, 1. So no change. If you use NOR gate, 0, 0, if you apply, no change. But here if you apply 1, 1, no change. Now you apply S equal to 0 and R equal to 1 in this diagram. Then S equal to 0, R equal to 1. Now how do you analyze this? If any one input is 0, then output will be 1. So therefore Q is equal to 1. If Q is 1, then what about Q bar? Q bar is 0, that's it. This is called a set state. This is set state, and this one is reset state. And again if you apply 1, 1, no change from the previous condition. But the problem is, again in this NAND gate construction also, if you apply 0, 0 here, then what is going to happen? If any one input is 0, output is 1. Here also if any one input is 0, output is 1. So this is not allowed. So this is something called forbidden state. Okay, so here both inputs are equal to 1, which are allowed. Okay, but if you apply 0, 0, then that is not allowed in the NAND gate. Okay, therefore this is the forbidden condition. So in the NAND gate construction, both inputs being equal to 0 at the same time are forbidden. So this kind of combination should be avoided. So theoretically you can develop a circuit like that, and you cannot ask the user okay do this and don't do that, like that and all. So somehow if by mistake or unfortunately if the things are happening, then your circuit will not work and nobody is going to buy your product. Okay, so somehow you need to modify the circuit, and so that even if 1, 1 comes or 0, 0 comes, somehow your circuit or your device or your technology has to work. So that is why people went to the next step. Okay, so let me write down some note about these two types. So in comparing to NAND with NOR latch, note that the input signals for NAND require complement of the complement of those values required for NOR latch. See, here the top one is reset and the bottom one is set, and here top one is set and bottom one is reset, right? And output is no problem. Okay, here also Q and here also Q bar. Now the beauty is, when S equal to 1, Q is 0, isn't it? But if you look at here, when S equal to 1, Q is 1, right? When S equal to 0, Q is 0. But here when S equal to 0, Q is 1. That means what? The NAND and NOR, there is a fundamental difference. Here if the inputs are SR and here the inputs are, if you want the same type of truth table, then input must be complemented. Therefore, if anyone wants to construct the same truth table of NOR gate from the NAND from the NOR latch, okay, I'm sorry, I'm confusing. Okay, if anyone wants to construct the truth table of NAND, truth table of SR latches using NAND from the truth table of NOR as like the truth table of latches which uses NOR, then the input has to be complemented. If you compare these truth tables, okay, I think you can show it now, but it's very little. Let me write down here SR Q bar, See, if this is 1 0, then here also 1 0, 0 1 0 1. This is for NOR. If you take NAND gate, then what is going to happen? SR Q Q bar. If SR is 1 0, then this is 0 1. This is 0 1, then this is 1 0. Okay, so that means what? If you compare this and that, so both are S bar and R bar. Okay, so you put the arrow mark like this. So this 0 becomes 1 if you invert it, and this 1 becomes 0. Similarly, this 1 is 0 here, this 0 is 1 here, complemented. So if inputs are complemented, then you get back the NOR operation, NOR operations truth table. Therefore, basically the latches used by NAND and NOR are same. The only difference is in the NAND gate you have to invert the input S bar and R bar. If you give like that, then there is no problem. Okay, because the NAND latch requires a 0 signal to change its state. But in NOR, that's what, okay, if any one input is 0, then you will analyze this in NAND gate. But in NOR gate, if any one input is logic 1, then you will start analyze. So this 1 and 0 are basically complement of each other. Therefore, the latch which is constructed by using NAND gate is sometimes called a S bar R bar latch, not SR latch, S bar R bar latch. Okay, so in order to designate the fact that the inputs must be either in their complement form to activate the circuit. So that's it about the latches. Now what is the drawback? In the first one is 1 1 is not allowed, forbidden, and in the second case 0 0 is not allowed. Then what should I do? I need to somehow modify the circuit. Now that we are going to look at how one can modify the circuit. So the next one is draw, insert pictures, then where is it? Yes, is this? No, SR latch with control, not this one. Discovered image. Insert pictures. Is this one? Yes, this one. Now we are going to analyze this. So how one can make sure that forbidden state is overcome. So with the help of enable input, let me take. Now the operation of the basic SR latch can be modified by providing an additional input. That additional input is called enable. Here EN stands for enable. Okay, EN stands for enable. That determines or controls when the state of the latch can be changed and determines whether S and R can affect the circuit. Therefore, S and R actually controls the output of the circuit, and this enable determines when that change has to be occurred. Therefore, this circuit consists of basically an SR latch and two additional AND gates. Okay, so I have two additional AND gates here. NAND gates. Now this control input EN act as an enable signal for the S input and R input. Now the important point is when enable is 0, then what is going to happen? The outputs of the NAND gates, this NAND gate is 1, right? If any one input is 0, then the output of the NAND gate is 1. Therefore the outputs of this NAND gate, let's say first NAND gate, second NAND gate, third NAND gate and fourth NAND gate. The output of the first NAND gate is 1, the output of the second NAND gate is 1, as long as the enable signal remains at logic 0, and this condition is called a quotient condition. This is called a quotient condition. Quotient condition for the SR latch. Now when the enable input goes to 1, then the information S input is passed to this point and R also passed to this point. How? Suppose you have two input AND gate. Now this is A and this is B. When I connect this B to like plus 3 volt, that means logic 1. So this is 1. What is this? AB. If B is 1, then this is equal to A. Therefore the A is transferred to the output when B is high. So here if you look at this point is 1, then this S is transferred here as S bar, and this R is transferred to this point as R bar, because this is NAND gate, right? So you have a NAND gate, 2 inputs, let's say A and B, and this point is AB bar. If B is 1, then this is A dot 1 whole bar. So A dot 1 is A, then A bar. So this A becomes A bar. So by the same token, this S becomes S bar in this point, and this R becomes R bar in this point. Therefore you are constructing basically SR latch SR latch, but the SR latch construction of SR latch using NAND gate. But what is happening here? The truth table is similar to whom? SR latch with a NOR gate. Okay, so that's what it is happening now. So by employing 2 more additional NAND gates and extra enable input, now we are going to get the truth table of SR latch, which is constructed by using NOR gate. Now again same operation, when S equal to 1 and R equal to 0, you can analyze it very easy. Now you can analyze this. Okay, so now the things are very easy now. Now let's say when the enable is 0, as I said, both are 1 no change in the previous state. 1 means no change, right? If you look at the table here, see 1 means, look at here, 1 means no change from the previous state. That is why in this case, if this is 0, then this is 1. If both are 1, no change from the previous state. When enable is 0, then no change. That's what you write, no change. Next state of Q is no change. Okay, so the first row of the function table is clear now. I went a little fast. Again, just I'll tell you, because this is slightly confusing topic. So it's not like combinational circuits. So see, when enable input is 0, if any one input is 0, then output is 1. If both the inputs are 1, if you go back to this, say this is again your good old friend of SR latch using NAND gates. Now if the input combination is 1 here, then no change from the previous state. Okay, no change. See, this 0 1 becomes 0 1, 1 0 becomes 1 0, no change. So that is why in this truth table, if enable input is 0, then this is XX. That means what? No change. XX means what? This S can be 0 0, 0 1, 1 0, 1 1, anything, don't care, doesn't matter, but the previous state will not be changed in the next state. That's it. So the first row is clear now. Now actually I copied this figure from the textbook, because I need to write and erase. If I draw the figure, then I cannot, it's very difficult for me to explain. Otherwise I could have drawn the figure. Fine. Now take the next state, this one. Enable input is 1 and this is 1. If any one input is 1, so then this point becomes S bar. If this R becomes this point, R bar. Okay, and if you, when S equal to 1 and R equal to 0, then S bar becomes 0 and R bar becomes 1. If any one input is 1, what is output? Output is 0. If Q bar is 0, what about the Q? Q is 1, right? So look at here, this is 1. Okay, so I didn't go with as per that. Okay, so let me I'm sorry, I'm moving here and there, so please forgive me. Let me take this second row. Let us explain the second row now. Enable input is 1. So this point is 1 and this point is 1. Now this is 0 and this is 0. What is going to happen? Then this is going to be, see, this point is S bar and this point is R bar basically. If enable input is 1, then this point is going to be S bar and this point is going to be R bar. So S bar becomes 1 and R bar becomes 1. When okay, if any one input is 1, then what is the case? Output is 0. What am I doing? 1 second, go back here. So 1 1, if both are 1 1, then output is not changing, so previous state, that's what it happened here. So if S bar is 1 and R bar is 1, then output will not change, no change in the previous state, no change. Okay, and take the next one. Is that clear? I don't know, because myself itself I am not convinced. See, the enable input is 1, S is 0 and R is 0. So this point is 1 and this point is 1. Now let's say Q is the previous state. Okay, this is 1 and this is 0. If this 0 is fed back here, if 1 and 0, 0. So because any one input is 0, the output is 1. So it changes from 1 to 1. Now this one is coming back here. Both inputs are 1. So output will be 0. So it moves from 0 to 0. So there is no change. So previously it was 1. Then after applying the input 1 1 1, then it is 1. Previously it was 0, now it becomes 0 0. So therefore no change. Second row is over, cleared. So like that you can verify the next row, third row. Now let us go to the third row. Third row. Now input is 1, this is 1, S is 0, so this is 1, right, and R is 1, so this point is 0. Now if any one input is 1, what is output? Output is 0. If Q is 0, then Q bar is 1. So this is what happening here. Therefore Q is 0. If Q is 0, that is called a reset state. Reset state. Fine. So enable input is 1, S is 0 and R is 1. So this 0 becomes 1 here because of this Nand gate, and this 1 becomes 0 here. If any one input is 1, then output will be, which way should I analyze? No, if any one input is 0, output will be 1. That's a operation of your Nand gate, right? Therefore if Q bar is 1, then what about Q? Q must be 0. So this is called a reset condition. Okay, so therefore third row is clear now. Now let us take the fourth row. Okay, so enable input is 1, S is 1, R is 0. So this 0 is going to be 1 in this point, this 1 is going to be 0 here. Now if any one input is 0, then output will be 1. If q is 1, then q bar is 0. So therefore q is 1 here. So this is called a set state. So that is the fourth row. Now the last one is fifth row. So let us see. The fifth row is 1 1, all are 1 1. This is 1, this is 1, this is 1. So this 1 becomes 0 here. This 1 becomes 0 here. Now if any one input is 0, then what is output? 0. Look at here, this also 0. Okay, don't say like some I'm sorry. If any one input is 0, output is 1. And this also 1. If both are 1 1, that is not allowed. Again there is a problem in this. So that is called an indeterminate state. So not allowed. So again there is a problem. Okay, so step by step we need to move on. Therefore, in this SR latch with the enable input, okay, so this is SR latch with the control input. Again this also has problem, because here indeterminate condition occurs when all three inputs are equal to 1, because this condition places zeros on both inputs, this point and this point. Okay, if all inputs are 1, what is happening? This is 1, this is 1, this is 1, and this point is 0 and this point is 0. So if both inputs are 0, then output becomes 1 1. So this is undefined state. When the enable input goes back to 0, one cannot conclusively determine the next state, because it depends on whether yes or R input goes to 0 first. Therefore this also has the problem. This indeterminate condition makes the circuit difficult to manage in practice. Therefore it is seldom used in practice. But nevertheless, the SR latch is an important circuit. Why? Because other useful latches and flip-flops are constructed on this basic circuit, basic SR latches. Okay, so even though this is not used in practice, but this is the basic understanding, and this is the one we need to build the useful one. So one has to be very thorough on this. And next let us discuss the D latch. Okay, how this difficulty is removed. So insert pictures, where is it, that guy, is this guy? I don't know. Let's see. No. Discard image. Then which one? Insert picture. Not on this one. Okay, let me draw the figure. It won't take much time. So I don't know where it is. Okay, so you put 4 NAND gates. NAND gates like this. This is Q bar. Sorry. This is, that is Q and Q bar, and this output is fed back here, and this one connected here, and this is connected here. You connect like this, and you connect these two guys, and this is enable, but the beauty is instead of having two inputs, I am going to have only one input by using a NOT GET, so that this NOT GET makes sure that both the inputs cannot be 1 1. All three inputs cannot be 1 1 at a time. That is why if you put a NOT GET, you cannot apply. Okay, so if you apply 1 here, then in this point 1, in this point 0, right? If you apply 0 here, then this point is 0 and this point is going to be 1 because of this NOT GET. So therefore, the forbidden state somehow you are trying to remove. That's what the people that thought and said, hey, don't give two inputs, don't take two inputs, take only one input, but internally connect these two inputs together through a NOT GET. Somehow this undetermined case can be removed. Okay, therefore one way to eliminate the undesirable condition of the indeterminate state in the previous case SR latch is to ensure that S and R never be equal to 1 at the same time, and this is done with the help of a NOT GET, and this is called D latch, and the nomenclature falls like D means data latch. Okay, so this latch has only two inputs, this is data and enable, that's all. There is no third input, but in the previous case you have three inputs, enable, S and R, but here I have only two inputs. So the D input goes directly to the S input of your SR latch, and its complemented input goes to the R. That is happening through the NOT GET. So as long as the enable input is at 0, the cross coupled SR latch has both inputs at the 0 level, and the circuit cannot change state regardless of the value of the D. Therefore, if you want to draw the truth, write down the truth table, enable, then data. So if you put 0, then if you whatever the condition, no change. It's very simple to analyze. Okay, the same analysis what we did in the previous case. You make enable 1, if you apply 0, then 0 comes here. Okay, Q is 0. This is called a reset state. You can analyze it. It's not a big deal. When enable is 1 and D is 1, then Q is 1. This is called a set state. Let me take 1. When enable is 1, so this point is 1, this point is 1, this point is 1. When D equal to 1, so D is 1, this also 1. When D is 1, then what about this point? This 1 comes here and here 1, and this is 0. Now what is your NAND gate? If any one input is 0, what is output? Output is 1. And this also 1 and this also 1. What is happening here? This is 0. So if any one input is 0, this 0 becomes 1 here. If Q is 1, then Q bar is 0. Q bar is 0. Therefore this is called a set state. That is why Q is become 1 here. Okay, so this 1 becomes 0 here and this 0 becomes 1 here. So this is called a set state. Like that you can analyze. Therefore why is it called a D latch? Because the D latch receives, or the D latch has the ability to hold data in its internal storage. Whatever you give here, the same thing appears here. That means it stores the data as long as the power is on. Okay, so it stores the data indefinitely. That is why this is called a D latch, data latch. It stores it. If you give 0, it stores 0. It holds 0. If you give 1, it holds 1. Okay, therefore it is suited for temporary storage for binary information between unit and its environment. Okay, so therefore the binary information present at the data input of the D latch is transferred to the Q output when the enable input is 1. Here the output follows the input. Okay, so here the output follows changes in the data input as long as the enable input is 1. And sometimes this is also called a transparent latch. Why is it called a transparent latch? Because the input is directly reflected in the output. Okay, when the enable input is 0, then there is no path between input and output. The binary information that was present in the data input, okay, will not be transferred to the output. Okay, so that's it. That's the operation of your SR latch, your D latch, data latch. Now one more point I would like to mention here. Instead of drawing the circuit, again and again, okay, either 4 NAND gates, 1 NOT gate, like that, one can draw the compact symbol. Okay, so one can draw the compact symbol, something called block diagram representation. This latch can be represented as a block. Okay, so something called graphical symbols for latches. So let us insert that. Insert pictures, reason, yes, this guy. Okay, now this is the SR latch. Draw. Okay, now set, reset. S and R stands for set and reset, and Q, and this is Q bar. Why this bubble? There is a small bubble. This bubble indicates complement. Okay, so the latch is designated by a rectangular box like this, with the inputs on the left hand side inputs, and the right hand side you have outputs. Because this type of block only we will be using at a later point of time in our course, especially when we design the counters. And one output designates normal. This is normal output, and this one is complemented output. Okay, bubble designation designates the complemented output, and this one is called a small circle. No, that circle is bubble. Okay, that bubble indicates complement. So this is SR latch. Yeah, SR latch, and this is S bar R bar latch. That means what? This is constructed with a NAND gate, and this is with the NOR gates, and this one is with enable and D input, D latch. This is, see, that's why the symbol comes here, D latch. So look at here, it has only 2 inputs, and here also 2 inputs, and here also 2 inputs. But here S and R, here you have only 1 input. This EN is enable, and this is normal output, and this is complemented output. But if you look at one small difference here, in the case of the SR latch construct using NAND gates, look at the input here. The input also bubbled. That means what? The input is complemented, right? So that's why you have written here S bar and R bar. Okay, so in the input also the bubbles are added to indicate that setting and resetting occur with the logic 0 signal. And this is a graphic symbol for D latch. Okay, the D latch has inputs D and EN, and EN indicates enable. Okay, so let me stop here. In the next lecture we will start flip-flops. We are going to discuss flip-flops. So this also your storage element. In fact, this is the one we are going to use in practice. So till now whatever we have discussed, this all are basics or fundamental. So the next one is the actual circuit which we use in our day-to-day life, in all your electronic gadgets like your mobile phones, cell phones, your computer, your PDA, your electronic consumable electronic machines, whatever you name it, everywhere we will use it, right? Starting right from your electronic watches. Okay, so thank you very much.